Okay, we're back. 14. And first of all, this must have been copied and pasted from before when I had several functions and I said they were all f of x, y, z, even though none of them depended on z. Yeah, this should just be a function of x and y. I meant to just say f of x, y. I mean, it's not like crazy for me to call this f of x, y, z if it doesn't depend on z, but that I didn't mean to do that. Anyway, sorry about that. So let's find its critical points. Here we go. The critical points is where the gradient is 0. I could find the whole gradient and set it equal to 0. Of course, the gradient is just all partial derivatives, so let me just individually find the partial derivatives and set them equal to 0. That's equivalent to setting the gradient equal to 0. So here I go. Partial with respect to x. And I see the product rule. I see something that depends on x and then something else that depends on x. So here we go. Product rule has two parts. Take the derivative of the first part with respect to x. It's just going to be a 2x because that y squared just goes away. And I leave the second thing alone. Plus, okay, now I'm going to leave the first part alone and do the derivative of the second part. The derivative of e to the negative x is e to the negative x times the derivative of the inside with respect to x, which is negative 1. And like I said, we're setting that equal to 0. And we're going to solve that, but let me write down our second equation first, because this is partial with respect to y. I have to set all the partial derivatives equal to 0. Okay, so here I go, and I'm happy to announce that I don't have any product rule here because this doesn't depend on y. So I'm just going to take the derivative of the part that does depend on y and leave that exactly the way it is. And so that equals 0. Okay, so I've got two equations. I'm tempted to clean the first one up, but let me actually postpone that. I like the looks of the second one. I'm going to deal with this first. Yeah, so, well, actually, here's how I'll phrase this. I've got a few things multiplied together and that equals 0. So I know that one of these things I'm multiplying together equals 0. I'm going to be very silly. Either 2 is 0, or y is 0, or e to the negative x is 0. I wrote that without thinking at all, especially this part. Obviously, that one's not the case. Well, this one could be the case. So this is something that we have to consider. So this will go on my list of things to consider, but let me move on. This one is almost as silly as saying 2 equals 0. This one never happens. If you don't see this and recognize it immediately, one way to think about it is, if I were to solve for x, the first thing I would do is the natural log of both sides. But the natural log of 0 is undefined. Trying to solve that for x would tell us that x equals something undefined. In other words, there's no solution for x there. So out of these three possibilities, only one of them is actually possible. So from this point on, we know that y has to be 0. That's going to be useful when I go up to the first equation, because I would like to know x. So let me go up to the first equation, 2x e to the negative x plus, and y is 0, so I'm just going to, and I've got this negative sign, so actually let me write minus x squared e to the negative x equals 0. Okay, let me factor this. Actually, I'll pull out an x and an e to the negative x. And then I've got a 2 minus x equals 0. Okay, now I have something factored, and I'm multiplying a few things, and the product equals 0, so one of these things must be 0. Either x is 0, or this is 0, and before I even... This one showed up just a minute ago. This one has no solution. This one's not going to be what leads us anywhere. But moving on down the list, or 2 minus x equals 0, so that one would give me x equals 2. Okay, so I've had 3 possibilities. One of them definitely didn't lead anywhere, but the other 2 are legit. So my critical points are, they're both going to involve y equals 0. One of them involves x equals 0. The other one involves x equals 2. So these are my critical points. We are also supposed to, where am I looking? Here we go. Characterize each critical point as a local max, local min, or neither. And basically that means use the second derivative test. Let's do the Hessian. Ooh, yeah, well, we'll see how bad this is. Let me leave myself a nice amount of space here. So for the Hessian, yeah, actually, let me, okay. We'll start the Hessian in just a second. The Hessian is this matrix full of second derivatives, and what was going through my head just a second ago was I was looking, because usually when you get to this point you've already found the first partial derivatives, and that'll help you find the second ones. And the thought that occurred to me is I probably should have simplified the first partial derivatives before I go and take the second ones. So here's especially this one. Right? So let me pull an e to the negative x out of everything. And then this is a 2x, and this has a minus on it, so minus x squared minus y squared. Maybe for this one there's nothing really to do, so I'll just write it that way. Okay. Now the Hessian is not going to be that fun, especially this one. Taking the derivative of this with respect to x, because this is going to be another product rule. I don't want to be a baby, but it's not going to be fun. Okay, let's do it. Product rule. Take the derivative of the first part. The derivative of e to the negative x is e to the negative x, and I have to multiply by the derivative of the inside, which is -1, because I'm doing the derivative with respect to x, times, and then I leave the second part alone, because I'm doing the product rule. Plus, and then I'm going to have an e to the negative x, and then I do the derivative of this with respect to x, which is 2 minus 2x. So that is e to the negative x times, negative 2x plus x squared plus y squared, when I do that all in there, plus 2 minus 2x. So x squared plus y squared minus 4x plus 2. Okay, and that's going to be one of the things that goes in our Hessian. Yeah, I think we're good. Let's do the Hessian now. I think all the other things that go in the Hessian are going to be easier. So this one is the partial with respect to x, and then x again, that goes in the top left. What goes here is the mixed partial. So there's a couple of ways I could do that. I could look here and do the partial with respect to y, but I don't like how this one looks. I would rather look here and do the partial with respect to x. So, or actually, yeah, neither one is that bad. But here, I'll do what I said anyway. This is going to be I'm doing the derivative with respect to x. So the 2y is going to stay, and then it's e to the negative x times negative 1. Same thing goes right down here. Actually, I'll simplify it when I put it down here, just to put the negative in front. And then what goes down here is the derivative with respect to y, and then y again. So I'm looking at this, and I'm doing the derivative of this with respect to y, which that's just going to take the y off, so 2e to the negative x. Okay, we have 2 points. I've got 0, 0. What do we get? Let's keep in mind e to the 0 is 1. So all of these e to the negative x's, they're all just 1. And so I'm plugging in 0 for x and 0 for y. So here I'm just going to get 1 times 2. So 2. Here I get, I guess this whole thing is just 0. This whole thing is just 0. And this is 2. I am using Sylvester's theorem. I draw my little corners. This one's positive. When I do my 2 by 2, I get 4 minus 0. That's also positive. Positive all the way through is positive definite. Positive definite means local min. Okay, moving on. At my other critical point was 2, 0. Well, okay, so 0 is going in for y and 2 is going in for x. So it looks like I've got a 4 minus 8 plus 2. Actually, let me not go too fast here. I've got an e to the negative 2 times 4 minus 8 plus 2. This is just going to be 0 because y is 0. This is the same. This is 2e to the negative 2. So what I've got here is negative 2e to the negative 2, 0, 0, and then 2e to the negative 2. So it's a bit weird. I've got e's going on in here, but let's just keep in mind, what is e to the negative 2? It's 1 over e squared, and e is like 2 point something something, so e squared is going to be like, I don't know, somewhere in between 4 and 9 for sure, because e is between 2 and 3, so the square is between 4 and 9. It's just a number that we don't need to worry too much about. Well, let's keep in mind that it is a positive number. E to the minus 2 is a positive number. So as I'm doing Sylvester's theorem, this is a positive number, but I have this negative sign in front of it, so this is negative. And meanwhile, if I do the 2 by 2, I get this times this minus this. And when I multiply these, I'm going to get negative 4e to the negative 4. Well, what is e to the negative 4? Again, that's 1 over e to the 4th. It doesn't matter too much, except it's a positive number. But I've got a negative 4 times that positive number, which is going to be negative. So how did this go? This went negative, negative. If this was going to be negative definite, then it would start negative and then it would alternate from there. So the next one would be positive. This is not negative definite because it didn't do that. This one didn't do it didn't do what it's supposed to do for positive definite or negative definite. So it's indefinite. So this is a saddle point. All right. Great. So, let's do something else. Yeah. We just did 14. Let's take a look at 16. We have this line integral. And it is parametrized as t squared, t goes from 0 to 1. So here's what let's call this f of t. dl is the magnitude of f prime of t dt, which is magnitude of, okay, here's f prime. I do the derivative of each thing with respect to t. So 1, 2t. It's magnitude of that. So let's do the magnitude. It involves a square root. I'm going to do this squared plus this squared. Let me go back to the integral we're doing. Finish setting it up. I'm going to integrate with respect to t. T is going to go from 0 to 1. I replace x with what it is. In this case, x is just t. I replace dl with what I just figured out. So now we've got this, which is actually a, we could even call this a Calc 1 problem, because this is not, I mean, it's not involving one of the more fancier integration techniques. This is just going to be a u substitution. I can let u be the inside of the square root. Du is 8t dt. And I like that because I've got this t here. So let me rewrite this. So, right, of course, this is just square root of u. And then for the t dt, yeah, maybe I don't need to do this, but because of this, t and dt is du over 8, so I took the t and the dt and replaced it with du over 8. I'm changing variables here, and I do have limits of integration. I'm going to do this the method where I change the limits of integration. The way this goes is, what goes here is I'm going to take this is a value of t, and I'm going to find the corresponding value of u, which would be 1 plus 4 times 0 squared, so that's just a 1. Likewise, what goes here is the value of u corresponding to 1, which is 1 plus 4 times 1 squared. So that's a 5. Okay. I can do this. The 1/8 can come all the way out. I'm doing the antiderivative of u to the 1/2, which is u to the 3/2, but then I put a 2/3 in front. And this is multiplication. And this is going to go from u equals 1 to u equals 5. Let me wrangle with the fractions just a little bit, do a little bit of canceling. So that fraction is just going to give me 1/12, and then I can plug in 5 and 1. So 5 to the 3/2 minus 1 to any power is 1, so I'll just write 1. And maybe I should think about how to simplify 5 to the 3/2, but actually the 2 in the denominator means I would do the square root, and then I'm not going to do the square root of 5. I don't have a calculator, so we're just going to leave our answer like this. Great. Then let's do the next thing. I'm going to evaluate this other kind of line integral. So, right, these are the two types of line integrals. And of course, I mean, it's always going to be a thing where I give you a line integral. I'm going to see people doing the wrong one, but you should try to do the right one. DL means the thing with the square root in it. That's the kind that we just did, because DL is like the magnitude of f prime, and magnitude has a square root in it. If you don't see DL, you're going to see something like dx and dy, and for dx, you're just going to do the derivative of whatever this x part is, and for dy, you're going to do the derivative of whatever this y part is. I would say this kind is easier. I don't like square roots, especially inside of integrals. It's not a fun time usually. So, actually, let me just set this up right away. It's going to be an integral with respect to t from 0 to 1. I've got a sine y here. I'm going to replace y with what y is here. So sine 2t. And then I'm supposed to multiply that by dx. Dx is just dt. I just want to do this a little bit slowly because I know some people seem to basically just replace the dx with dt and the dy with dt without really thinking about it. Dx is dt in this case because x is just t. If x was like t squared, then dx would be 2t dt. Like I have to do the derivative of whatever this is and put it here. In this case, it's just dt. But I don't do that carelessly. I actually think about it. So here I go. Here's the next part. E to the x. So I'm going to, instead of x, I'm going to write what x is in terms of t, which is just t. And then I'm supposed to multiply this by dy, which is not quite just dt. It's 2 dt. Because I have to do the derivative of what this is. That's where the 2 comes from. Okay, now this is just a Calc 1 problem. I think I can do this right off the bat here. The antiderivative of sine would normally be negative cosine. If I have a 2 here, the way I fix that is with a 1/2. What I'm doing here is I'm skipping the work of a very simple u substitution. If you prefer to go through the work of letting u equal 2t and then carrying out that u substitution, you'll get this. But the shortcut is to just, if I have a constant times t in here, and like instead of sine t, I have sine 2t, then the 2 stays on the inside and I do 1 over that constant on the outside. That's the shortcut I remember. This is just 2e to the t. I got 0 and 1. Okay, so the rest is very boring. Not that the previous part was terribly exciting. So I'm putting in 1 for t. Here's putting in 0 for t. Of course, cosine of 0 is 1. E to the 0 is also 1. So it looks like I've got this. So negative 1/2 cosine 2 plus 2e minus, this is 3/2. Great. Okay, what do I have left? All right, I'm gonna cut this off and make one more video out of these.